The news landed with a thud. In the early days of March 2026, a stark and unexpected bulletin that rippled from the plains of West Texas to the trading floors of Wall Street. OpenAI and its partner, Oracle, had pulled the plug. Their ambitious plan to dramatically expand the massive Stargate data center in Abilene, Texas, was officially on hold. The reason was not a failure of innovation, a bug in the code, or a shortage of the world's most advanced silicon. The reason was far more fundamental, far more mundane. The local power grid simply could not deliver the electricity required to fuel their next great leap forward. The smartest machines ever built are being defeated by 100-year-old copper wires. This single announcement crystallized a crisis quietly building for years. A slow-motion collision between exponential AI growth and the unyielding limits of industrial-age infrastructure. The story of AI in 2026 is no longer just about algorithms, data, or petaflops. It has become a story about raw energy, about transformers, substations, and the transmission lines that underpin civilization. The race for AI supremacy has become, in essence, a bare-knuckled fight for electricity. The numbers at the heart of this crisis are so large they can be difficult to comprehend. We're not talking about gradual, predictable growth that utilities can plan for over decades. This is an explosive, almost vertical shift in demand, driven by a technological revolution that is unfolding in real time. The canceled expansion in Abilene was just one part of a larger project, a canary in the coal mine for a much bigger problem. It was a single campus that, combined with other planned facilities, would consume gigawatts of power, straining regional grids to their breaking point. To make this tangible, let's focus on a single, concrete figure: 1.2 gigawatts. This is the estimated power draw for a state-of-the-art AI cluster. A massive, unified system comprising about 1 million of the latest GPUs, all working in concert. For context, 1 gigawatt is the typical output of a large nuclear plant, or a massive natural gas station. These are billion-dollar infrastructure projects that take years, sometimes over a decade, to build. A city like San Diego can hit 2 to 3 gigawatts on a hot summer day. One AI cluster at 1.2 gigawatts is city-scale power, but unlike a city, it runs at full throttle, 24/7, 365 days a year. It's a concentrated, relentless load. Drop a new city's worth of constant load onto a rural substation designed for a small town, and you risk destabilizing the entire local grid. The workhorse behind this demand is NVIDIA's Blackwell, a marvel of engineering designed specifically for training and running the largest neural networks. Hyperscalers like Microsoft, Google, and Amazon envision clusters networking 1 million of these chips to build the next generation of AI models. Each chip draws significant power, hundreds of watts just for the processor, plus more for its high-bandwidth memory and the surrounding board components. You pack dozens of these servers into a single cabinet, and suddenly you have 50 to 100 kilowatts per rack, the power of several homes concentrated in the space of a refrigerator. Fill a data hall with these racks, and the load pushes into tens of megawatts. String multiple halls together on one campus, and you're at the gigawatt scale. But the power draw is only half the story. The other half is heat, because for every watt used to compute, another watt, or even more, often goes to cooling and support systems. All that compute power becomes heat. 1 million high-powered space heaters in one building. The thermal challenge is immense. Engineers battle against thermal resistance, the friction that prevents heat from escaping the chip's core. The heat flux, or the density of this energy, is so high that traditional air cooling simply can't keep up. B200 thermal resistance. Why heat wins? The thermal path runs junction to case, R theta JC, then case to cold plate, R theta CS, into coolant, through pumps and heat exchangers, and finally, the facility loop to ambient. B200 pushes extreme power density and hotspot flux. Air's convective coefficient is limited. Pushing more CFM means higher fan power, more noise, and lower mean time between failures. Direct liquid cooling lifts heat transfer at the chip by roughly 10 to 20 times versus air, holds a tighter delta T, sustains higher clocks, and reduces throttling events. At 1 gigawatt campuses, liquid loops cut fan energy, lower PUE, reduce hall temperatures, and shrink footprint. Reliability comes from manifold redundancy, leak detection, and isolation valves. For dense GPU racks, liquid is no longer optional. It is a design prerequisite. This is why liquid cooling is now mandatory at the gigawatt scale. Industrial scale systems, chilled water loops, gigantic air handlers, massive chiller plants devour power too. The energy needed just for pumping the coolant becomes a significant factor in the facility's overall efficiency and reliability. It's a vicious cycle. The more you compute, the more heat you generate, and the more power you need just to remove that heat, which adds to your total energy bill. You can't just say yes to a 1.2 gigawatt load. The entire plant-to-outlet pathway must be meticulously analyzed, and in most cases, completely rebuilt. This means new high-voltage transmission lines, upgraded distribution lines, and brand new substations with massive transformers, a multi-year process involving physical work and long-lead procurement for critical components. Faced with delays beyond a year, and more likely a 3 to 5 year timeline for the necessary grid upgrades, the Abilene plan stalled. The result? A standoff. The future of artificial intelligence is waiting at the gate, but the power isn't ready to let it in. This is the basic math behind the AI power crisis. The problem extends far beyond the walls of the data center. The insatiable demand for compute power is colliding with the physical realities of our electrical grid, creating a series of cascading bottlenecks that threaten to stall the entire AI revolution. To connect 1.2 gigawatts, you need copper, everywhere. It's the fundamental conductor, the lifeblood of the grid. From the massive high-voltage transmission lines that span continents, to the underground cables that feed our cities, and even down to the delicate windings inside every single transformer. But global supply chains for specialized copper components, like high-voltage cables, are stretched to a breaking point. The result is a monumental traffic jam. Approximately 2,300 gigawatts of new projects, mostly renewables and storage, sit stuck in interconnection queues across the country. Before any project can connect, utilities must conduct lengthy studies. These often demand significant grid upgrades, triggering a scramble for already scarce materials and specialized labor. This is the copper bottleneck in action. If copper is the grid's circulatory system, then large power transformers are its vital organs. These are not off-the-shelf items. They are massive, custom-engineered steel boxes filled with oil and meticulously wound copper coils, indispensable for grid stability. They enable efficient high-voltage transmission over long distances, and then step that power down for safe end use. You cannot build a data center without them. There is no software patch for physics, and their lead times have become astronomical. Industry surveys report 128 weeks on average, 144 weeks or more for larger, more complex units. That's nearly 3 years. Approve a new data center campus today, and your critical transformers may not land on site until 2028 or 29. The reasons are systemic. Very few factories worldwide can build these giants. Supply chains for essential inputs like grain-oriented electrical steel and copper are congested, while demand explodes from every direction. Utilities are replacing their aging fleets, new renewable projects need to connect, and the electrification of transport and industry accelerates. Each of these sectors needs transformers, all at the same time. Then add the unprecedented demand from AI campuses, each requiring multiple large transformers to function. The financial consequences are staggering. A 2-year delay can represent $120 to $160 million in deferred revenue per campus. For hyperscalers building dozens of these sites at once, these delays defer billions of dollars in revenue per year. The transformer shortage is no longer just a supply chain headache. It's a multi-billion-dollar bottleneck throttling the world's AI timelines. This physical constraint is now spilling into the political arena. Massive AI loads create zero-sum fights for finite grid capacity, sparking fierce political backlash from communities and incumbent industries. In March 2026, a voluntary industry pledge emerged to coordinate grid requests. Yet experts doubt its effectiveness without formal rules and enforcement mechanisms. Policy is diverging wildly by state. Some are trying to fast-track approvals, while others are imposing moratoriums or forcing data center developers to fund the entire cost of grid upgrades. Suddenly, navigating local and state energy policy is now a core competency for AI site selection and corporate strategy. 3 Mile Island Restart. What it takes. First, ownership and partnership. Microsoft backs power procurement, but an NRC-licensed operator must execute the restart and hold the operating license. NRC hurdles begin with license status, Part 50 or Part 54, requiring a license transfer or renewal, and updates to the plant's safety basis before restart. The final safety analysis report must be updated for restart conditions, and NEPA environmental review may trigger a supplemental EIS if the scope has changed. Physical security and cybersecurity plans must be modernized, and the emergency preparedness program fully reconstituted with drills and staffing. After a long shutdown, aging management and equipment qualification are critical. Pressure boundary inspections, component replacements, and turbine generator overhauls. Grid and market. PJM must restudy interconnection, accredit capacity, and assign transmission upgrades with cost allocation, plus state oversight and public comment. Timeline and CapEx realities. Licensing, engineering, procurement, and construction stack, measured in years, not months. Why SMRs aren't ready before 2029. Many designs still await certification. COL or ESP processes add site-specific reviews and hearings, extending schedules. Factory module supply chains are not yet scaled. QA programs and auditors are still maturing for nuclear-grade fabrication. First-of-a-kind risk drives financing challenges, and HALEU fuel availability remains a gating constraint for several designs. The realistic path is late-decade demonstrations, with earliest commercial scale near 2029 and beyond. For hyperscalers, that means interim reliance on gas-fired microgrids and PPAs, bridging compute roadmaps until nuclear options mature. The immense heat generated by these AI clusters creates what the industry calls a thermal crisis. Not about comfort, it's a fundamental engineering limit. Traditional racks, 5 to 10 kilowatts. Modern AI racks can draw 10 times that. Concentrated heat creates failure points. If cooling falters for moments, GPUs throttle or shut down. At scale, exhaust overwhelms HVAC, triggering cascading failures. Hot aisles, cold aisles. Air is a carefully managed resource. Beyond chips, high currents strain PDUs, bus bars, and wiring. If not sized and cooled properly, they can literally melt. Protection trips interrupt million-dollar training runs. Many older data centers can't support this density. Build new or retrofit at high cost. The thermal crisis is a hidden tax on AI's progress, paid in watts, steel, and coolant. Compute begets heat. Heat begets more power draw, and the bill keeps rising. After examining staggering power requirements, grid bottlenecks, desperate workarounds, and new hardware, the defining battle for AI won't be won by code alone. The winner will control vast, reliable electrical power. Success now demands mastery of heavy industry, generation, high-voltage engineering, and transformer logistics. Negotiating PPAs and permitting microgrids now matter as much as elegant code. Those securing gigawatts, from the grid, private gas, or SMRs, will train larger models and deploy at scale. Those stuck in interconnection queues, waiting years for transformers, will be left behind. Power has become the strategic moat of AI. Watch where data centers rise. Watch transformer lead times. Watch efficient hardware. When a company announces its next AI breakthrough, where are they getting the power? The race for compute has become a race for power, and the winner will hold the keys to the future. 3 stocks to watch. Signals, not hype. NVIDIA, ticker NVDA. Performance per watt leadership and network stacks drive demand. Vertiv, ticker VRT. Exposure to liquid cooling, power distribution, and full data center integration. Constellation Energy, ticker CEG. nuclear generation and long-duration PPAs for hyperscalers. In a world where compute appetite compounds faster than the grid, should AI growth be gated by carbon-free megawatts available, or should we accept private gas and nuclear restarts to sustain innovation? Share your take below. Thoughtful analysis over ticker hype.